Recall we said last day, Ryan, that the magnetic force on a particle moving perpendicularly to a magnetic field can be calculated by, well, it's a force. What was the symbol for magnetic field? What letter did we use for magnetic field? B, so that's why I always go FB. I could go FM, FB. And we said, Grant, that it was given by the charge, the speed, and the size of the magnetic field, which is a vector, except these had to be perpendicular to each other. Charge is a scalar, so it has no direction, so I'm not putting a perpendicular sign beneath the charge. So consider an electron as follows. This is my scrawled diagram. But I think what we have is an electron moving which direction? To the right? Entering a magnetic field. And which way is the magnetic field pointing? What do those X's mean? Okay, into the page. Now, an electron moving to the right, we don't deal with an electron moving to the right. That's the same as a proton moving to the left. So point your right thumbs to the left. You have an S, you too? Point your right thumbs to the left. Yes? And the magnetic field is into the page. Which way will this electron experience a force? Okay, right when it gets here, it's going to get pushed down. Now the electron is traveling kind of slanty down. That's the same as a proton traveling slanty up. So all of us, let's point our thumbs slanty up, fingers still into the page. And I think the electron experiences a force slanty down left. Yes? And now it's traveling straight down. That's the same as a proton traveling straight up. Now the electron experiences a force straight left. In fact, I think if I continue this, hey, the electron will be forced into technically a semicircle, but okay. That's important. You know why, Ashley? It means that we can say, what path is this electron tracing out? We can say magnetic force equals centripetal force. And I know a number of us struggled with centripetal force, but this is a nice review since we're getting towards the end of the year and your final exam is only about a month away. Hey, good, we could kind of be reviewing some of this. And you'll notice we've been reusing a lot of the concepts in Physics 12 all year long anyways. We've been doing force, for example, in almost every unit, no matter, just different versions, different variations of it. It means we can say this, QVB equals mv squared over r. Don't forget the mass, because force is mass times acceleration. Or qvb equals m4 pi squared r over t squared. Why does that work, Rachel? Because we really said this. QVB equals MAC, because force is MA, so centripetal force is MAC, circular, centripetal. Now, hey, this is the big one. In fact, we're not going to be using the one with the period in it in this particular unit. And this is the beginnings of particle physics. Here's what it says. For example, if you measure the radius of a charge coming in, you can calculate either its speed or its mass, depending on what else you measure. Ooh. And if we start knowing its mass, we can make a good estimate as to what this magic particle might be. Example 2. An electron moving at 3.2 times 10 to the 6th enters a perpendicular magnetic field and traces out a circular path. What's the radius of this path? Well, magnetism is pushing this in a circle. The magnetic force is what's pushing the electron in a circle. And magnetic force is QVB. And since they gave me a speed it's going to be mass times the acceleration with the speed in it. Oh, and grant it turns out one of those will cancel because there's a v on top on the left and there's a v squared on top on the right. They're both on the top. What's this question wanting me to find? Oh, let's get the r by itself. It's on the bottom. I don't like that. How can I get it to the top? Let's move the r to there. I think we'll get this. R equals, there's an mv all over qb. Is that right? By the way, just since we're talking about final exam review, what's mass times velocity? That's something we've studied. What? Oh! But actually now you have a way of discovering the momentum of a particle too. Even if you don't know the mass. The momentum would be QBR. Q would be the charge. B would, you know, the magnetic field, you've created it. Radius you can measure from taking a picture or whatever. Anyways, let's keep going here. M, it's an electron. V, oh, speed. Q, it's an electron. Oh, Grant's on the job. Excellent. Hey. Times 10 to the negative 19. B, oh, magnetic field, 0.545. Now, I made up these numbers, and I think you end up with a really small, yucky radius, because I keep forgetting to change the numbers in this question, and it's been like 6 years, and each time I come to this question, I go, oh, yeah. But I can't remember. Let me see. Unless I finally did remember to change it and forgot that I remembered to change it. Divided by 1.6, negative 19, times 0.545. You get 3.34 times 10 to negative 5. That's a really small radius. That's like a micro, that's less than a micromillimeter. Anyways, sorry, I made up bad numbers. 3.34 times 10 to the negative, 3.34 times 10 to the negative 5 meters. What else could I, oh, I love this question. I love this question. This idea of having a magnetic field bend a particle into a circle, Sam, it's going to be on your test. But as far as I'm concerned, I can either ask you to find the charge or the magnetic field required or the mass of the particle or the speed that it's incoming or the radius, all depending on what information that I give you. So in example 3, we have the same idea. We're bending a charge into a radius. Hey, let's double check. Is the diagram right? This charge at the bottom here, positive or negative? And when it enters the magnetic field, what direction is it traveling? Up the page? Point your thumb up to the page. What direction is the magnetic field? Will it get deflected this way, this? Oh yeah, it will. So the diagram is right. It's also a chance for us to practice our right-hand motor rule. So as shown in the above diagram, a proton entered a magnetic field at location A. The radius is that when the magnetic field strength was that. What's the proton's speed? You know what, McKinley? I'm going to start this off the same way. The magnetic force is what's pushing me in a circle. QVB equals mv squared over r. Luna, I'm being a bit sloppy. I should have double-checked. Hey, is the velocity and the magnetic field at right angles? Yeah, the velocity is up the page and magnetic field's into the page. That is a right angle. There is going to be a force. Will you ever give us one where there isn't? Not on the written section. I won't try and trick you. What's this question asking me to find? Oh, get the V by itself. One of them canceled. How would I move the M over? Divide. How would I move the R over? Okay. So it looks like I'm going to get this. V equals Q times B times M. No, not times M, times R, Mr. Dueck. Divide by M. Q, it's a proton. 1.6 times 10 to the negative 19. B in Teslas, they told me 0.02. That's 2 times 10 to the negative 2, but that's a lot less writing. R, the radius, 3.25. M, the mass, it's a proton. Okay. How fast was this proton as it traveling as it came in? And we're getting the speed because the direction is changing. So I'm not going to try and... Oh, in a circle would be my direction, I guess. Yeah, we got some kids coming through. You get 6.23 times 10. 1, 2, 3, 4, 5, 6. 6.23 times 10 to the 6th. Units. Oh, it all comes back to meters per second. Look at that. So these are the kinds of questions that I can ask you for a moving charge. But you'll recall last class I showed you the video of a jumping wire. A bunch of charges locked inside of a wire. What's the force on that? So the magnetic force on a current carrying wire. If we have a wire that's carrying a current perpendicular to an external magnetic field, it will also experience a force. How big? The direction of the force can be calculated using the right-hand rotor rule. Point your thumb, extend your fingers, palm points in the direction of the force. The magnitude depends on 3 things. You know what? I can actually derive this one. If you want to write over here the one force equation that we do have, this is the same as distance over time times b. If the speed is constant, there's a direction change, but not a speed change, because it's going in a circle at a constant speed. I'm going to move the T underneath the Q. Hey, what is Q over T? It's on your test next class. Current. Ooh, now we got something we can work with in a wire. The magnetic force on a current carrying wire depends on 3 things. It depends on the magnetic field. Right there, see it? It depends on the distance. Now, what's the distance? Well, first of all, it depends on that there, which is the current. And it depends on some kind of a distance. Which kind of a distance? We're going to use a lowercase l. The length of wire in the field. Not the total length of wire, but whatever chunk of it is inside the magnetic field. F equals Bill. See it popping out? There's the B, there's the I, and there's the, which distance? The length of the wire. Oh, except all 3 of these have to be at right angles. It has to be current this way, fingers this way, palm that way. Or current this way, fingers this way, palm that way. All three have to be at right angles to each other. So example 4. Find the magnetic force and direction on the wire. Okay. Notice what I said, Emma. We have the current going this way. Magnetic field is going to be this way. I guess the length doesn't have to be at right angles. It's really the current and the magnetic field and the force have to be at right angles. So you can cross out the little perpendicular there. My mistake. Well, let's get the magnitude. F is equal to Bill. Looking at this picture, how big is the magnetic field? Huge. Remember the MRI machine was 4 Teslas. This is big. 6. How big is the current? 5 amps. Pretty big. How much wire is inside the magnetic field? 0.7. Grant is reaching for his calculator and disappointing me. I'm going to go 6 times 5 is 30. 3 times 7 is 21. 30 times 0.7, I'm pretty sure, is also 21 newtons. Is it not? Mm-hmm. Direction. Okay, how do we figure out the direction? This is the third right-hand rule. Point your right thumbs in the direction of the current. Point your fingers like you're high-fiving in the direction of the magnetic field. Now this one's a little awkward. I go like this. I'm either going to do that, or I'm going to do that, or I'm going to move my paper, which is probably what I would do. But no matter which way, do I end up with my palm facing into the page? Right? That way, into the page. Suppose the force on a 5 centimeter piece of wire carrying 12 amps is that many newtons. What's the magnetic field strength of the perpendicular field through which it passes? Okay. Like always, Emma, anytime I give you an equation, as far as I'm concerned, since this equation has 4 variables. By the way, I always make my lowercase l written because I'm worried if I do that, what does that look like? A 1. So a good habit to get into. Put a big loop in there so you know it's an L. It's got 4 variables. Marissa, as far as I'm concerned, then you can find any missing any of those. I give you 3, find the 4th. In this case, Marissa, what are they asking me to find? Don't. Okay, magnetic field strength. Say it again. What are they asking me to find? What variable is that? A lot of kids want to say, isn't it F? No, that's magnetic force. Which of these is magnetic field? B. How do I get the B by itself? I guess the magnetic field is going to be the force the wire experiences divided by IL. It's going to be 1 times 10 to the negative 3 divided by 12 divided by, careful, am I going to put a 5 down there? 0.05. 1 times 10 to the negative 3, that's 0.001, which is less typing, divided by bracket 12 times 0.05. This is going to be 0.1616. Oh, my decimals are off. 0.001. 1.67 times 10 to the negative 1, 2, 3. Is that right? Units, magnetic field, Teslas. Here's our new unit. Whoops. Okay, we have a distraction, but we're all back now. Some neat applications. Some neat applications. Can we deal with the distractions, boys and girls? A movie came out about 20 years ago now, based on a book by Tom Clancy called The Hunt for Red October. Anybody seen the movie? Because it was a classic. Okay. Here's the physics of the Magneto hydrodynamic drive that they talk about. In theory, and they're working on this, you could build a submarine that moves through the water with no moving parts, which would mean the submarine would be very quiet. And if you don't think both Russia and the US want quiet submarines, hey, you're crazy. So how would this work? Instead of a wire, you use the seawater as your conductor. So I'm going to pause the video because I got to stand up. So they're working on that. They may have it already because the book is 20 years old and the theory is already about 30 years old or 40 years. I don't know. If they did, I'm sure it's classified somewhere. Moving on. A solenoid. We have said that a solenoid is a group of wires coiled together in the same direction, often around an iron core. This one doesn't have an iron core. And it becomes an electromagnet. We figured out the direction of the magnetic field using our right-hand rule, holding the solenoid in our hand. How big a magnetic field can we create? Here's your next equation. So you have the following variables in a solenoid. The number of turns of wire, the more times you wrap it, the stronger it's going to be. How long the solenoid is. If you make it long, it gets weaker. If you cram the wires together, if you make it shorter, you get a much stronger overlapping magnetic field. The current, if you send more current through the solenoid, you're going to get a bigger magnet. And the magnetic field strength is what we're trying to figure out. So Ampere determined, well, you know what? He found the following. He said, okay, the magnetic field from a solenoid is proportional to or depends on, here's what he noticed. More turns makes it stronger. In fact, if you have 2 turns, you're twice as strong. If you have 100 turns, you're 100 times as strong. If you wrap it around 1,000 times, you're now 1,000 times as strong. And Ryan, that's nice because that basically gives us a magnetic field that we can control ahead of time. You want it stronger? How much stronger? How many more turns do I need to do? How many more wraps of wire do I need to do? He said it also depended on the current. As the current got bigger, the magnetic field got stronger. But he found as the solenoid got longer, the magnetic field got weaker. So he said, if you cram the wires together, Sam, so they overlap more, you get a stronger magnetic field. And then he said, but I'd like to replace this with an equal sign. He needed a constant. Very similar to big G, which was 6.67 times 10 to the negative 11. Very similar to K, which was 9 times 10 to the 9th. Here it is, folks, your last constant of the year. But it's one of the best ones. In fact, it does have, to me, the best name of any constant. Next page. So he found magnetic field from a solenoid depended on the number of times you wrapped it around, N for number of times you wrapped it around. The current, but it was inversely dependent on the length. Shorter was stronger, longer was weaker. Similar to, hey, here's your gravitational field, here's your electric field, but recall in both of those we needed to introduce a constant, big G and little k. We have to do the same thing here. Here's your equation. Magnetic field from a solenoid is equal to mu naught. You can say mu 0, but you'll sound way more impressive if you say mu naught. And I had a British high school physics teacher who was one of my heroes as a teacher, so in his honor, I'll always pronounce it mu naught. N-I over L. Where mu naught is on your formula sheet. How big is it? Ashley, what? 4 pi times 10 to the negative 7. Now, first of all, you should get a little nerdy adrenaline rush. What the heck does pi have to do with magnets and magnetic fields? The universe seems to like that number. And it has one of the best names of any constant. You've just learned the permeability of free space. McKinley, what did you learn in school today? Mummy, I learned all about the permeability of free space. Oh, McKinley, you are ever so clever. Thank you, Mummy. Okay. Put your pencils down, look up. There's a second version of this equation on your formula sheet. Sometimes, instead of knowing the total number of turns of wire around the solenoid and how long the solenoid is, instead what they do is they give it to you as a ratio. They just tell you how many turns per meter. So you can also see mu naught I think it's n times I. I'm freezing. I'm going from memory. Can I see your formula sheet, Ashley? I'm having a brain blank. Don't know if I have to do this, but I am now. Yeah. Had me worried for a second there. Where n is the number of turns per, oh, that's terrible, per meter. These look very confusing. They're not. They're mostly plug and chug. Let's start applying some of this. So, a solenoid is carrying a current of 4.2 amps. If the solenoid is 1.2 centimeters long and is made up of 750 turns of wire, what's the magnetic field at its center? Underline the word solenoid. What are they asking me to find here? Magnetic field. What's the symbol we're using for magnetic field? Not F. That's force. Yep. And B from a solenoid is equal to mu naught N I over L. That's right from your formula sheet. This one I want all of you to try on your calculator because some of your calculators might deal with pi strangely. Mu naught is 4 pi times 10 to the negative 7. N is the number of turns of wire. How many turns of wire in this question? 750. I is the current, 4.2, all divided by L, 0.012. Try typing that in. Some of you, the Casios, for example, you may get an error. If you do, let me know. On my calculator, I can go 4 pi scientific notation button, negative 7 times 750 times 4.2 divided by 0.012. And I get that. Who gets the error? So those of you that got the error, the issue is your calculator doesn't know how to use pi followed by scientific notation. So what you folks will have to type instead of 4 pi times 10 to negative 7 is pi 4 times 10 to negative 7. Pi times 4 times 10 to negative 7. Pi times 4? I don't think you should. Let me pause the video and come look at what you're typing. Don't clear your screen. So some of you have to type pi times 4 times 10 to negative 7, scientific notation button, negative 7. Some of you, I know the TIs, the software can handle the 4 pi followed by it. Anyways, we get a magnetic field of 0.33 Teslas. And you don't realize just how handy this is. What if instead of a magnetic field of 0.33, what if I wanted a magnetic field twice as big, 0.66? I could call the factory up and I could pre-order it. They would say, oh, Okay, we'll put, instead of 750 turns of wire, we'll put 1,500 turns of wire. We can customize ahead of time, Emma, in an electronic device. We can customize the magnetic field that we want. Or, sorry, our circuit doesn't have 4.2 amps. Well, tell me how many amps your circuit has. I can customize then how many turns of wire we need to put around the solenoid in the factory. Whatever magnetic field you need, we can build. It's very customizable. Oh, and as before, as far as I'm concerned, Rachel, there's 1, 2, 3, 4 variables, because that's a constant. I can give you any 3, find the 4th one. Example 8. Find the field and the direction at the center of the coil. Let's do the direction first. So what this is a picture of, you're all looking right down the solenoid, okay? That's why there's just a single circle. Really, if you wanted to, you could imagine that the solenoid kind of extends like that, and there's a bunch of turns of wire. Like, I just didn't bother drawing that in. So what direction is the magnetic field? Hold that solenoid in your hand. Now, to hold this solenoid in my hand, I'm either going to hold it this way or this way, because the solenoid itself is going into the page. Curl your fingers in the direction of the current. Jake, which way is your thumb pointing? You know what? The magnetic field coming out of the page towards us, right? You said north was up, and magnetic fields point from north, so coming at us. Okay, we got the direction. Check. How big? Well, the magnetic field from a solenoid is equal to mu naught N I over L. Did they give us the current? Yep. Did they tell us how long the solenoid was? No. So, cross that one out. There's a second version of this equation. The second version, which is also on your formula sheet, is this one. Little n times I, where little n is the number of turns or wraps or coils per meter. Did they give us the number of turns or wraps or coils per meter? That's when you use this one. And you'll know because they didn't tell me a length, either in the picture or in the question. 4 pi times 10 to the negative 7, the permeability of free space. What a great name for a constant. 2,550 coils per meter. And this one is carrying 10 amps. Again, try these on your calculator. Make sure you know how to type in that 4 pi times 10 to the negative 7. Some you got to reverse it. And I get a magnetic field of 0.032 Teslas. And again, let me emphasize, Sam, just how nice this is for creating your own magnetic field. You want a magnetic field twice as strong? You can do it 2 ways. Double the current, if your circuit will allow it. And we've just finished our unit on circuitry, so you know how we have the ability to basically force feed any current that we want to. Or double the number of turns of wire. You want it weaker? Same idea. It's customizable now. I think this is the last one. Yep. A solenoid is to be wound on a cardboard form 30 centimeters long. How many, so here's the factory question. You're a car company and you're building a solenoid in your engine. And you know that you have room for 30 centimeters. And you know that you need a magnetic field of 6.28 times 10 to the negative 3 Teslas. And you know that you're going to be getting 5 amps from your car circuit. So now if you're Ford, how many turns of wire do you want to put around that solenoid? Okay. So the magnetic field from from a solenoid is mu naught Ni over L. Otla, what are they asking me to find in this question? How many turns of wire, which is which variable in here? Do a process of elimination. Is it that one? No. Is it current? No. Is it the length? No. That's a constant. Oh, you know what they're asking me to find? N. How would I get N by itself? Times the L, divide the I, and the mu naught. The number of turns is going to be B times L divided by N times I. It's our N, Mr. Dueck? Mu naught times I. Yo. So little n is the number of turns per meter. It's actually a ratio. So in other words, this here might have 500 turns. I don't know. But they would rate it as, if there was 500 turns in this distance, it would be rated as however many turns per meter. I'd have to do the math and kind of make a rough guess. Probably about 10,000 turns per meter. It's going to be B, 6.28 times 10 to the negative 3, L, 0.3, 4 pi times 10 to the negative 7, 5 amps. How many turns of wire would this solenoid need? $300? Or, Otla, little n would be 300 turns for 30 centimeters. You would need a solenoid with a rating of 1,000 turns per meter. That's the difference between it. So 300 turns for a 30 centimeter long wire. Or you would say to the factory, look, have you got a solenoid that has 1,000 turns per meter? That's what I need. And if I put that in there with a current of 5 amps, I'll still get my 6.28 times 10 to the negative 3 Tesla magnetic field. What's your homework? Number 1. Number 2, here we have a wire, and it says that balanced gravity and magnetic forces. Number 2, you're going to start out by saying gravity is equal to magnetic force. So number 2 is good. 3 is good. 4 is tricky. 5 is good. 6 is good. 7 is good. Skipping 8, 9 is good. 10 is good. 11.